Welcome to this session. In today's session, we will learn about the chemistry of some fused heterocycles, quinoline and isoquinoline. In our previous session, we have learned the chemistry of pyrrole, thiophene and furan and one 6-membered heterocycle, pyridine. And today, we will learn the chemistry of isoquinoline and quinoline, in which one pyridine ring is fused with one benzene ring. So let us start. So in today's session we will focus on the chemistry of quinoline, and as you can see here in the structure that this is the structure of quinoline and this is the structure of isoquinoline. The difference is at the level of the position of nitrogen in the ring. Here one 6-membered heterocyclic containing nitrogen atom that was in pyridine is fused with the benzene ring. So the difference in quinoline and isoquinoline is the position of nitrogen. Both of these heterocycles are isolated from coal tar and bone oil fractions, and they can be separated by other fractions of coal tar by fractional distillation because they have the higher boiling points. So boiling points of quinoline is 237 and isoquinoline is 243. Due to their highly boiling points and their basic nature, these two heterocycles sometimes also used as solvents in organic synthesis for doing the reaction at high temperatures as a basic solvent. So these heterocycles have very big importance in chemistry because there is one very interesting molecule you can see here. This is the part of quinoline, and this is the very well known molecule of quinine. This quinine molecule is an alkaloid and it is very well known for its anti-malarial activity, and for more than 200 just 100 years back, this was the only medicine for malaria which was using the natural medicine for malaria. Still quinine is very frontline important medicine for malaria, and the malaria which are resistant from quinine, for that we have some other molecules. And this is also very well known famous example, the ciprofloxacin. Ciprofloxacin is an broad-spectrum antibiotic that is comes under the class of fluoroquinolones. So this moiety is also contains this heterocyclic nucleus. So many more drugs, many more medicines, dyes and many compounds of important from application point of view, they contains the quinoline and isoquinoline nucleus, so they are important. Now we will see how these molecules can be synthesized in laboratory and what is the process of mechanism of formation of these molecules. So if you want, you can write these structures. We will start with the synthesis of quinoline derivatives. So we will study three main synthesis of quinoline, and the first one is scrap synthesis. Just I will give you a brief introduction of this scrap synthesis. Scrap synthesis of quinoline is a very important reaction to use in laboratory for synthesis of heterocycle. This reaction involves the heating of aniline with the glycerol, Apart from glycerol and aniline, we use little amount of ferrous sulfate, concentrated H2SO4 and nitrobenzene in this reaction. And slowly I will show what is the role of all these reagents in the chemistry. So aniline and glycerol, these two are reactants. Nitrobenzene, sulfuric acid are reagent. Ferrous sulfate is used to slow down the reaction process because reaction is very violent. So to retard or slow down the reaction process, we use some iron to sulfate. So the reaction comes on the paper is, we have aniline plus CHOH, CHOH, CH2OH. This is glycerol. We use sulfuric acid. We use ferrous sulfate. We use nitrobenzene. And just we have to heat both of these reactants. And the product will be isoquinoline, no, not quinoline heterocyclic. Actually, nitrobenzene is used for dehydration. In last step, there is a step of dehydration. I will show in the mechanism. So this is the reaction. You can write. See, writing is very important in organic chemistry while understanding the mechanisms, because once you will write by your own in your copy, you will be able to understand more clearly how the migration of electrons and how the reactants are combining to give the products. So although it is good you watch the videos to see the how the reaction is going, but writing is also very important for you to learn the mechanism. So once all these two reactants will combine to form the product, and we will see how the reaction is going. Actually, the most important first step in the reaction is oxidation of this glycerol, and this glycerol oxidizes into acrolein by removal of water molecule, and the reagent which carry out this change is H2SO4. As you know that sulfuric acid is known for its dehydrating property and for oxidation. So the first step is CH2OH, CHOH and CH2OH. Oxidation H2SO4, when it will treated with H2SO4, it will undergo dehydration reaction and it forms, it oxidizes to aldehyde CHO. This compound is known as acrolein. This is the first step, the oxidation of glycerol, and this is the reason why we need to heat gently. Once we mix reagent and start heating, very soon this glycerol is converted to acrolein to have the aldehyde. Now you can see that we have a conjugated system, the double bond alkene and the carbonyl. So this conjugated system will undergo Mannich reaction, conjugate 1,4 conjugate addition, and we will see how. I am removing some part of this. So okay. So you see we have aniline. Aniline and this is going to react with CH2 CH, this aldehyde. This is the mechanism of conjugate addition. Once carbonyl is in conjugation with the double bond, it goes not 1 2 1 2, not 1 2 1 2 3 4 1 4 addition. So this is known as 1 4 addition. We have a nucleophile, and this nucleophile is adding to the double bond is moving, and this carbonyl is moving. This is example of 1 4 addition or 1 4 conjugate addition. So this will lead to the formation of this is the one proton will remove from this NH2 and it will be taken up by this minus charge. So this is alkene and this is alcohol. This can undergo tautomerization to form the keto form. Not keto, because it is a hydrogen here, so it will be aldehyde, tautomerized. This is a very important intermediate and it has been isolated successfully, and that is characterized that there is a formation of this aldehyde during the process of scrap synthesis. So now it will be again the addition on the carbonyl carbon to give the product remember there is a one hydrogen, don't forget that. There will be plus charge. Okay, so it will minus H plus again the benzene ring is restored. We are using H2SO4 sulfuric acid, that powerful dehydrating agent. This will lead to again removal of water molecule minus H2O. So we will end up with this compound, and remember in very beginning I told you that there is a step of dehydrogenation or aromatization or oxidation, what you can say, and this after removal of hydrogen we get the quinoline molecule. So what do you think? Organic chemistry is not interesting? You see how in very decorative manner these electrons are moving, and finally we end up with the desired molecule. So this is one of the synthesis of quinoline, and there is a couple of synthesis more for quinoline. We will see. If you want to write, you can write it. The other synthesis is known as Friedlander synthesis. This synthesis is reported in 1882. This synthesis, from synthetic point of view, this synthesis was not succeed very much because it was involving the orthoaminobenzaldehyde or aminobenzaldehyde, and generally the aminobenzaldehydes are difficult to prepare. If you see, this is benzaldehyde, and when you have amine at position, this is orthoaminobenzaldehyde, and since you have both the functional groups, the the aldehyde and amine in the same molecule, so it is difficult to prepare them in laboratory and from a stability point of view. So scope of this synthesis is limited, and the other reagent or reactant for this is a carbonyl compound which have alpha proton, like CH3CHO. Okay, we have a carbonyl. This can be aldehyde or ketone, and it must have an alpha carbon, and we need a strong base in this reaction. So one reactant is aminobenzaldehyde, one reactant is, you can say, acetaldehyde, which have alpha proton and a strong base. Then we end up with this is quinoline molecule. So one reactant is aminobenzaldehyde, one is carbonyl with alpha proton, or here we take the acetaldehyde. Reaction leads a strong base and leads the formation of quinoline. Now we will see how the reaction is going on. We have a carbonyl, then you know very well that how the reaction of this primary amine and carbonyl undergoes. They form shift base or imine, Clear? This will react with, and you can say minus H2O. This removal of water molecule. And after removal of this water molecule, it will form imine. Now the role of base comes in the picture. We have the base and we have this CH3, and due to presence of this imine, it will abstract the proton and will generate an anion. Is clear? Then again, this is a very simple reaction. You see carbonyl and there is anion. This will cyclize the ring. Okay? You can write plus H plus or minus H plus. H plus, base has H plus, and that will go on the oxygen to form the, and then of course there will be removal of water molecule, minus H2O. You have proton here. With this, you see, finally we end up with our desired product, the quinoline. Clear? You can write it. Okay. Now we will see another important synthesis of quinoline. And the name of this synthesis is quinoline synthesis. This synthesis was reported in very long back, the 1856. One thing you might have noticed that in heterocyclic chemistry, starting from very beginning, we are using one reactant which is common in the synthesis of all the heterocycles, that is ethyl acetoacetate. So with this observation, you can imagine the utility of this reagent, ethyl acetoacetate or active methylene compound. So again, in the synthesis of this non-quinoline synthesis, we will use the ethyl acetoacetate and aniline. You see how? Plus this is aniline and this is EAA or ethyl acetoacetate. Now, so we will end up with the compound. What we want to prepare is we will see how. This is the reaction. What we will do. I think in the end we will have hydroxy here. Okay, we will see what we will have. Just this this is the beauty of mechanism. When we write the mechanism, we got to know the exact product, what is going to form in the reaction. So let us start. If aniline and thiacetoacetate is reacting, and it used some acid catalyst, we use in this reaction. So this is the ester. This functional group is ester, COOC2H5, ethyl ester. So if we have an acid and amine, it can undergo ester hydrolysis. Ester hydrolysis. This will break, and when it will break, then amine will react here to form the amide. Ester will hydrolyze and it will convert into amide due to presence of this primary amine. So what we will have as a product, this okay, how? Just minus, you can say minus C2H5OH. This part is removing from the molecule by ester hydrolysis, and then again acid is combining with the amine to form the amide. So we have a amide linkage, this in place of this ester, and here one carbonyl. Now this carbonyl will undergo 1,2 addition to form the product.